Yeah, so you're because Val unfortunately has back pains, and I know exactly what it means when you get a crisis, when you have back pain, you have to lay down. You cannot force it, you cannot push it. There is nothing you can do. So so that's it. So he won't be able to give this lecture. This happened late last night, so I'm totally unprepared. I don't have any slides. I could have taken some old slides, but I think it's actually a great idea for us to spend some informal time, some black time. And I would like to start by discussing what you should all start worrying about in these final presentations. My plan is to have the final presentation on October 30th.
Wait, November?
November is better.
Everyone's awake.
Which is a Thursday. We have 14 people registered. If anybody wants to give an additional presentation, that's fine too. With 14 people times 15, this is more like 3 hours and a little bit. My plan is to have each of you give a presentation for under 50 minutes including questions. So to be on the safe side, I'd like to have this a 4 hours event. I depend on you because you can help me reserve a room. I need a room with a projector and nice chairs. Do you see any concerns with Thursday, November 30th, which is 1 week after Thanksgiving?
Maybe it's just a little bit long to be in a room for 4 hours.
We will take breaks. Absolutely. Okay. Yeah, it's going to be like a mini conference. We take breaks. We will get organized.
What about we have?
Is it not possible to split it up into like 2 sessions?
Absolutely, we will have 2 sessions, but I don't want to split it up in 2 days because usually the second day everybody is tired. Let's keep it intense in 1 day. There aren't that many. 14 short presentations should be doable. I've done this in other classes as well, and it gets intense, but it's also doable. So I depend a lot on Joe, but my plan, this is what I usually do, is that I have a little competition. Who gives the most attractive presentation? And each of you will vote. The rule is you cannot vote on your own presentation. And at the end, we will choose a winner. The professors also have a vote, and that vote might count a little bit more. But it's not based only on content. It's really based on the how good you give the presentation. There will be a little prize, some reward for the best presentation. That we encourage each of you to not just prepare a good presentation, but also participate and challenge the others and use your own judgment on how to evaluate presentations. So it's kind of time to start looking into what topics you want to cover. And I listed some on the website. The 0-1 laws are a fantastic topic. You would have to read this from Begin's original paper or from Lipkin's book. It's something you could compress in 12 minutes. You need to work very hard to make it exciting in 12 minutes to capture the 0-1 laws. Fagin also has this absolutely famous result that second order logic captures exactly NP, which some people, I think including myself, consider it even more elegant than the statement that satisfiability is complete for NP. It's nothing, Fagin's result that second order logic captures NP doesn't use any notion of Turing machines or any notion of computation. Its logic captures exactly this computation complexity class. Beautiful, beautiful result. And that is there like a 4 or 5. About some of those topics I actually don't know too much, but I know that they sound quite exciting. In addition, if you have any research project that touches a little bit on theory, you needed to learn about chase, a particular kind of chase, or a particular theory of query equivalence. That's what you present. Tell us about the exciting part of your research. Yeah, so it can be anything that is theoretical. And I don't remember if we decided whether you should be able to team up or whether this is individual. I'm happy to go either way. You want to team up in pairs of two if you have a colleague, or rather go individual. Don't make it complicated. Just do it individually. But if you decide to team up, I won't object. Anything that's fun for everyone to listen to. Okay, and nothing is confirmed. I'm waiting for Joe to, maybe I'll try. We need to find a room. This is a major bottleneck. I hope we can find a room on November 30th, but wait for the confirmation. Good. So is there any special topics that you would like to understand better that we can discuss on the whiteboard?
Would you consider having the presentation assignments?
Presentation. That's a good idea.
Because I don't think there will be many people left, so there will be interested people, and we don't have competition for reason.
Right. That's a cool idea. Let's look into this, and then we can reserve the 140 whatever.
Yeah,
146. Cool idea. And Grace, you should give a presentation too. Hello, Grace.
Just Grace.
She went to get.
I intend to.
Okay, good. Okay. You remind me, prompt me to make the reservation for the room.
Okay.
Okay, so anything special that you want to discuss that you would like to dig deeper into from the homework, from the course, from the lectures that we covered? I have something in mind that I'd like to discuss. You seem to be waiting for my opinion. Here's what I would like to discuss. I'd like to revisit the worst-case optimal join, which is going to be fast, and then talk about hypertree decomposition. That was a plan to cover in one of the earlier lectures. We didn't get there, and I'd like to try my best to cover this topic. Yeah. Okay, so let's talk about worst-case optimal join. And let me tell you what I teach in every undergraduate class, like in lecture 2 or 3. So I show them a SQL query. I mean, as a template of a SQL query. Select something from relation 1, x1, relation n, xn, where here a complicated condition. And I ask the students, look, we need to agree on what this query means. And it can get complicated. Maybe the word condition has a complicated subquery. So we need to agree on what this means. And here is what it means. We call it a nested loop semantics. The meaning of this query is that you iterate. I mean, it should be the same as iterating for x1 in R1. Then for each of them, iterate for x2 in R2. And for each of them, iterate after, have n nested loops, iterate for xn in Rn. And here you check if the where condition. If the where condition is true, then output the result. Yeah, this is the nested loop semantics of SQL query. And I tell the class, of course, the database systems are much smarter. They don't do it this way. And everybody agrees, and they are happy that they will learn about indexes and optimizations. So then we move on, and we talk about, let me write this here because that's important. We spent several lectures about optimization, and we draw these complicated plans. This would be a bushy plan, and here you push down the index, and you select from R3, and here you have another join. And you know all the tricks. You need to do a cardinality estimation and the cost estimation. You consider multiple alternative plans, and that is a state of the art that we teach over and over in all the undergraduate classes and the graduate classes as well. This is how how database systems work. And then in the most advanced classes, like this one here, we teach them that the best queries, the best algorithm for evaluating query, the work is optimal join, looks like this. How does it look? How does the worst case optimal join look like? Nested loops. But what's the difference from this? Why is it as naive as no lecture one and undergraduate?
Sort of folding the ifs up into the ins, so to speak. You're doing intersections to sort of partially satisfy the conditions. So by the time you yield, there's no condition to check anymore. You just yield it.
Very good. That is exactly correct. If all these conditions are joint conditions, then indeed the worst case optimal join for these joint conditions inside the for loops. There is a second, I think it's a fundamental distinction. Here we iterate over tuples. In worst case optimal join, we iterate over attributes, over the variables. So that looks like this, the worst case optimal join. It's for, and I should have used here T, but now I'm going to use, let me use Z. So Z1 in, and here it gets a little bit complicated because we need to intersect all those relations Ri, where Z1 is in the variables of Ri. And actually, we intersect its projection on Z1. This is critical, this restriction, and this needs to be done in time. In what runtime do we need to do this? This is important. You can't use merge join to do this intersection.
Size is the relation.
It's the smaller size of the relation. This needs to be done in time, which is the minimum over I of the size of R I dot Z1. And then we continue the same way for V2, and here we have to restrict the variables that already contain Z1 and so on. This is for schizophrenia join. It's an interesting narrative. The most naive execution that everybody loves at, so we can motivate all the complicated optimization techniques, and then we close the circle and we say that actually the optimal algorithm is this one. Okay, now here is a question. Suppose that we have an acyclic query. So let me draw it through the query graph. Actually, let me first write the query. So we have a query x, y, z, u, and this is r of x, y, join s of y, z, join t, z, u. Let's put another one, v, join k of u. Would you evaluate this query using worst case optimal? Let me turn this around. Suppose we evaluate this query using worst case optimal join. And every relation has size n. So the size of R is the size of S. It's the size of T is the size of K. And it's equal to, here I like to use red for the cardinality to warn us this is important, this is bigger. So in that case, what is the runtime of the worst case optimal join? What is the guaranteed runtime? We don't know exactly how fast it runs, but we have an upper bound on the runtime. You know how to compute this, no? You look for a fractional edge cover. What's the optimal fractional edge cover here? When you need to cover X, you need to put 1 here. You need to cover B. So you put a 1, and then you need to cover G somehow. So the worst case optimal will run in time, which is n cubed. This is something that you should not do. What is how should I put it, state-of-the-art algorithm since 50 years ago for computing acyclic queries? Yanakakis algorithm. So Yanakakis, how does that work for this query? How does Yanakakis algorithm work? Who can describe this as a high level? Describe it to an undergraduate student who want that person quickly for Yanakakis algorithm work. Yes.
You get a join tree, and then you do the semi-joins down, and then you do it back up or something.
Perfect. Yeah. So you do a semi-join down, which means that you retain from S only those variable y that appear in R. Just will decrease the size of S. Then with that decreased size, you retain from T only those T's that occur in S. Similarly for K. And actually, I showed you the second pass. And Dan Molteanu corrected me. You actually don't need the second pass. Once you've done this reduction, you can start to doing the joint from right to left. And the answer is guaranteed to be what? What is the runtime of Yanakakis? So Yanakakis algorithm runs in what time? In what sense is Yanakakis algorithm better? Yes.
Go till the input plus output.
Input plus output, exactly. So it's going to be n. And plus its mysterious output. So which one is better? N cube or this?
Bottom one.
The bottom one. How would you describe these two? What is the relation between these two?
When the output is a full join, then it's n cubed. But when it's less than that, it's less.
Perfect. The output can be as bad as n cube. We know this, and we know how to produce it. You look at for the fractional edge packing, and we know how to construct an artificial instance for which the output is as big as n cube. But in practice, if the user asks for this query, probably they don't expect an n cube output, so it is going to be much more efficient to run it this way. Okay, good. So this actually makes you think. On one hand, we praise the worst case optimal join a lot. On the other hand, it's not good at all for the most practical queries. What about something in between? What if we have a query that is neither, it doesn't seem to fit in any of these two conditions. So let me show you the query graph first. I want it to look like this. Now I can fill in the query. So it's going to be Q of X, Y, Z, U. Is R of X and Y. And S of Y, Z. And E of Z, U. And K of U, V. So what can we do here?
UX.
UX. Thank you. It's actually super important. This UX. Can we use that Yanakakis? We're not out of the box. Any suggestions? But there is a methodology. This is where I'm getting. When you already know it, but not let me.
Variable elimination? Sort of like
elimination, yes, which is equivalent to 3D composition. You solve the homework on 3D composition. Okay, so it goes like this. So I'm going to start using this board. We are going to create a joint tree, which is no longer going to be an acyclic joint tree like we had for Yanakakis, but we are going to place two or more atoms in the same bag. So let me place R of X, Y, and S of Y, Z in one bag. And separately, place T of ZU and K of UX in the second bag. It's a very simple example. Maybe I should have made it a little bit more interesting. Can I change it? Let me change it a little bit. let me add this edge. So this is going to be called L. So I also have L of Zx. So I need to include the atom L somewhere. Where do I put L? Let's put it as the top. And L of Zx. The previous 3D composition also works, but I think this is slightly more interesting. Okay, so in Yanaki's algorithm, we need to construct a joint tree where every node has a single atom. We cannot do it for a query that has these cycles, but we can approximate it with a tree where the three nodes, which are called bags, might have multiple atoms. In fact, they have multiple variables, but it's important that we also keep track of the atoms where these variables are coming from. And importantly, the running intersection property still holds. Running intersection property says that for every variable, the set of three nodes where that variable occurs must be connected. In this case, it's almost trivial because there's no way to disconnect these two. But if you have a more complicated 3D composition, you need to satisfy this condition that all the for every variable, the set of three nodes where it appears must be connected. Yes, Remy.
Yeah, so I think K should be U and X, so there's no U.
Yeah, oh, sorry. This is UX.
And so are you also allowed to put L also in the second bag?
Yeah.
Okay, so we're not bound to that. Yeah.
That's what we want to do. So now, but how do we use this to evaluate the query? Which is not acyclic, but it doesn't seem to be fully cyclic either. So it seems to be in between. You're looking at that 3D composition and how would you use that 3D composition together with the data that we have. Yes?
Can you try just computing the join using something else within each bag, and then you do the semi-join thing again?
Perfect. That is exactly how we do it in two steps. First of all, we compute each bag separately. So this bag will compute a view. Oh, these are brand new markers and they're horrible. It's not better.
Maybe you can like shake it or something.
Shake it?
It's like color. Yeah, the ink hasn't like fully.
You tried. Okay. Black is to be okay. Oh, you have a better one?
Maybe, not sure.
Looks better.
Point back here.
So A of is much better. A of X, Y, E is equal to the query R, X, Y and S, Y, Z and L, Z, X. And we separately compute this back. B of DUX is P of TU and K of UX. And then after you finish computing this back, we are in good shape because the new query Q, which depends on X, Y, Z, and U, is simply the join of A, X, Y, Z, and B, Z, U, X, and this is acyclic.
So when you say you do vertical join inside the bubbles, it seems like we're still missing an opportunity to like push the semi-join into vertical join.
Right. This is something that Hank does, and I don't have a good intuition how this is done, but it's a very good point. When you do the semi-join, okay, I don't know where to start. You see that you can start to explore how can you do the semi-join in a smart way. I want to just do the basics.
In this case, it seems relatively straightforward. I mean, you don't, you say you don't have to have done either join first, like for the top bubble, just ensure that the X's appear in K, right? And that costs nothing, right? You might as well do it.
It's a good point. So you could try to aggressively push the semi-joins.
So, you know, obviously the X's have to appear in K in the result, right? So in our first join, the top bubble, you might as well just add K as an atom and then just, you know, ignore the U.
Yes.
Right. And then you can do the same thing with T as well. And that costs nothing because it's just linear time.
Yeah, so I think 100, if I understand, is actually quite simple. So we take K and then we project only X. So we have the projection of K onto X and we put it in the other packet.
Yes.
Yeah.
Okay. Very good. This is something I can understand and we can discuss it in detail. Yes.
For the bottom bag, why do we need worst case optimal join?
For the bottom bar, that's the question that I want to get. So what are the complexities? All the relations have size n. What is the complexity of the top query?
1.5.
And to the n to the power 3 by 2. What is the complexity of the bottom query?
That's squared right now.
N squared. And once we are done, what is the complexity of the final query, of the ACK query?
Input is at worst n squared.
Yeah, so it's the size of the input plus output, right? It's input plus output. And our input now, it can be as big as n squared. So this is O of n squared plus the output.
I guess my question is like, why can't we use like now the bottom bag is acyclic, so why can't we use Yanakakis for the bottom bag as well?
Good point. So you could use Yanakakis for the bottom bag. I agree. And then that would be n plus this output plus the final output. But we can do something smarter, which was already alluded. Now, I placed L arbitrarily in the first bag. What can we do instead?
You just duplicate it again, right?
Repeat it here. So, also place L here, L of X. So now suddenly, if we add L of Cx, now it decreases from n squared to n to the 3 by 2.
And that's the same trick that we were discussing earlier, right? Of like importing the atom from one into the other. Just here using the whole atom.
Yes, but the trick you mentioned, or Rini mentioned, goes a step even further.
Yes, you have to project something out.
Yeah. So is this clear so far? Yeah. So what we want to minimize the AGM bound for each of the bags. This is the tree we're looking for, the one that minimizes the AGM bound for every bag. But we can go further. It's not going to minimize the AGM bound, but it's going to improve the practice. So this X also occurs in K. So we can also join this with K of underscore and X. I should have put it in green. So we can join this with K of don't care and X. Yeah, so I can add here K of don't care and X. This is the effect of the semi-join. And this is what Remy mentioned, that Hunt does at relational AI in their system. With the same trick, we also want to include here whatever we get from the top. Right, so we include the projection of R on X, the projection of L on X. Notice that we do not use a variable U here. We don't want U to occur here. But this means that we are projecting X pretty much like we were projecting it in the worst case optimal join, pretty much like we do in the semi-join reduction. We project on X and we further restrict the domain. This will not improve the asymptotic complexity unless you know something about the domain of X. If you plug that into the interim formula, then you might get something better. But if you only know the cardinalities, it's not going to improve that complexity. But in practice, it can be better. Yes, really.
Yeah, so I think if we, so here we're assuming everything has size n.
Yes.
So if you know that, for example, k and n are much smaller, then this, we can find a different cover. So say we know k and s has little n. So now the first bag becomes a little n squared instead of big N to the 0 over 2.
Yes. The right way to do is to compute the AGM bound for each query. And the observation is that the more atoms you add, as long as you don't add new variables, the more atoms you add, the more fractional edge covers you can have. And this can only improve the bound. Here we only, and with black, we only had 2 atoms. So the only fractional edge cover was obtained by placing 1 and 1 on each atom. We add a third one, and now we can place half, half, half. If you add more, depending on their sizes, that opens up for even more fractional edge covers, and that can be even better. Okay, so this brings me to the topic that I wanted to discuss, which is hyper-tree decomposition.
And do people kind of like use like bloom filters or other data structures to optimize this K business?
You could use so I know that for semi-joint reduction, sometimes people do use bloom filters. I wouldn't know how to explain it here. What is the right way to do it? But whenever you do a semi-joint, you have the option to reduce significantly the cost of the semi-joint by replacing it with a bloom filter. So how does a bloom filter work? I want to do the semi-joint with K. And Eugene suggested we use a bloom filter. Who can explain how would that work? And how would that improve over projecting over the column X of K and doing the join over here?
Very quickly know whether X is inside K or not.
Exactly. So we first need to pre-process K to iterate over the entire K and construct a bloom filter. Hopefully we can reuse it. But that bloom filter is very small. And it can tell us quickly if a given X is in K. If it is, it will answer yes. If not, it will answer maybe yes, maybe no.
It's the other way around, right? If it's not inside it, it will definitely answer no.
If it's not inside it, no. Then it might answer yes. If it's not inside, you might have a collision, no?
Oh wait,
Yeah, false positive.
oh yes, that's true. Yeah, I don't know.
Yes, but the bloom filter is very small. That's the advantage, and you can tune its size versus positive ratio. But now when you iterate over the axis here, you can check in that small bloom filter to see if there is any hope. If the answer is no, you're guaranteed to be able to ignore that X. So I think that's what I can say about bloom filters. They are much smaller. You can send them over the network. It's a major advantage. Yeah, Ramin.
Yeah, sorry for interrupting. I love this topic.
Okay.
So I know system people also really love bloom filters. So in terms of research, Harris has a new paper. I think it's a cited paper on using bloom filters to do exactly this. And then also Jignesh Patel from Wisconsin also has a paper. And someone told me that maybe this is secret, but now I know this. The SQL Server actually uses bloom filters to do this. To correct bad join ordering. So you can have a bad join ordering. It will take some higher up tables and then build a bloom filter and then pre-filter out some tuples.
Jignesh is limited to like snowflakes.
Sorry?
Jignesh is limited to snowflakes.
I see. Yeah.
Jignesh is what?
Their trick is limited to snowflakes.
So snowflake very fancy.
Right.
Yeah, so regarding what you mentioned about SQL Server, if you're looking for a paper on query optimization, the only one I can point you to is a survey by Surajit Chaudhuri in 1998. So this is 25 years ago, exactly 25 years ago. It appeared in PODS. It's a very good paper. And one of the, but it's still, it's 25 years old. It doesn't talk about the cascades framework, for example, which is fundamental. But one thing that he talks about is about semi-joints, which were still kind of fuzzy at that time and not very well understood in the Sigma community. Semi-joints is what we understand now very well. If you think about a very complicated queries, SQL query, with nested queries, with aggregates, and if you examine it closely, you can find opportunities for taking one table from this part of the query and semi-joining it, semi-joining a table inside based on the columns from the other table. So there are opportunities for doing such semi-joins. And this paper has one of these complicated examples, the SQL and aggregates, where it does semi-joins. I don't think it's secret. I think this is, it's technology that has been introduced to SQL Server a long time ago. Good. So that brings us a question. How do we do hyper-tree decomposition in general? And how do we measure its quality? So let's come up with a definition. Trying to use this. So definition. So we have a hypergraph. This is a query. But I think it's better if we are rigorous here and we call the hypergraph as a set of vertices and a set of edges. This is the query. Can you still see on Zoom? Yeah, this should be clear. Then a tree decomposition, sometimes called hyper-tree. Hyper-tree decomposition is, so bear with me because I'm not an expert and I haven't read this recently, so we need to improvise a little bit. What I know for sure is that you don't want to place only atoms on the nodes, but you also want to place variables. So I think the definition, which I remember from the paper by Gottlob and Fischler, is the following. So it is a triple E, lambda and rho, where no, actually, let me take it back. I'm not sure I need lambda. So let's put here a question mark. So here is a tree. Is a tree. Its nodes are called bags. Confusing term, but this is standard since tree decompositions were invented. Row. So here is what I'm gambling a little bit. I think it's fine just to define a row from the nodes of T into a set of variables. Yeah, so for each bag, we have a set of variables. We don't have yet these atoms. And another condition is a running intersection. It has other names. Running intersection. Which says that for every variable x in V, in the three nodes, the set of three nodes n, and let me be precise here, in nodes of T, where x occurs, so x is in row of n, is connected. Connected.
Don't you need some guarantee that relations map to a bag or something.
Exactly. So how would you suggest that? With right now I can make this empty. Nothing tells me I can make this empty. Yes.
All the variables for every relation, the set of variables needs to be in at least one bag or something.
Perfect. That is the condition. So let's write it mathematically. So for every edge, which is a relation, for every edge, there exists a node in T, such that E belongs to row of N. And that's it. This is a 3D composition.
So the question, so like going back to the previous example, the question of what relations to put in each bucket is no longer a question. It's induced by the set of variables.
Exactly. It's kind of induced. The way the best paper to read about this is a paper by also by Hung. So Hung no on FAQ, but look for the archive version. Not the POTS version, because you want the extended version, and they have it's two pages. I printed them and I forgot them in the printer. It's 2 pages where they describe the theory of hyper 3D composition, which consists of this and another thing that I want to show you before we take a break. It's a lovely text that essentially tells you everything you need. Okay, and the way they build there is now we need to worry about the cost, right? So how good is a 3D composition? By the way, does every hypergraph have a 3D composition? How will you do it, Chris? One single big bag, put all the variables there and you're done, okay? Obviously we want better. So we need a measure of how good we are doing. And now you start hesitating, how should we measure this? And the beauty is you can abstract this away. Now I realize you can call that rho, but I'm going to call it C, cost. So let's see a function that for every subset of variables gives us a positive real number. This is a cost. We decide later what the C can be, and then we call that another definition, the hyper 3 width of E is the maximum over all nodes n in the tree of the cost of rho of n. Easier here, right? Once we have the tree, and we only have the variables with the promise that every atom occurs somewhere. Once we have the tree, we just apply our function C. We see how much the cost is for each bag. The maximum is the cost of that 3D composition. And finally, the hyper 3 width of the hypergraph H is, if I just look at the hypergraph and I want to say how tree like this is, what is a hyper 3 width? How would you define it? The minimum, the best hyper 3 you can find. So the minimum over all trees T of the hyper 3 width of T for Q. Let me write it like this for H. T is a hyper 3 decomposition of H. I'm going to write it like in logical notation. T is a model of H. Yes.
I have a question. So how does C capture the interactions between bags? Because it seems like the output size depends on how the overlaps are kind of gonna blow up your final output size. And it seems like C is like a very local measure.
Let's see what C can be, and then we will come back to your question. So what can C be? How would you define C of a subset of variables? How should I call it? X, capital X. X is a subset of B. I want to write here because people on Zoom might not see that part. So given this set, what should C of X be? Let me offer the naive version. The traditional 3D composition of a graph says that this is the size of row of X, not the row, just the size of X. The size of X plus 1. The number of variables that you put on the node plus 1. It might be one. This is the standard mathematical definition of a tree width. It talks about the 3D composition of a graph, not a hypergraph, and this is a standard definition. Why is it plus 1? Look at this graph here. Let's make it. Let me draw it. X, Y, Z, U, and I'm going to add another one and V here. What is a 3D composition of, in our case, it's also hyper 3D composition of this? The graph is not. No. What condition is? It's very slippery. It's very misleading. What is a condition that this attempt to define it as a 3D composition fails? Which of the bullets? Every variable occurs in a connected component. We are good, but there is a bullet which fails.
The last one.
The last one. Every edge must occur somewhere. No edge occurs anywhere. So what would be a good 3D composition for something as simple as an acyclic graph? Exactly, we need to place here the edges. So we start with X, Y, Y, Z, Z, U, and where do I place ZV? I can place it anywhere. Let me place it here.
UV.
Right.
ZV.
ZV, that's right.
Oh, that's the covariance.
Yeah, that's it, right. So now you see that I need to subtract 1. So I'm looking at the number of variables in each bag. Subtract 1, and that is the natural definition of the tree width.
That's plus 1 over there.
It should
Oh.
be.
Okay. It's minus 1. Sorry. Okay. Yeah, this is why you were confused. So backtrack. So we take C to be the size of X is minus 1, and then that recovers precisely the tree width of a 3 to be 1. This is one possibility. A second possibility was to say that C of X is the edge cover. Edge cover of the subset X and E. Edge cover means an integral edge cover. So if you look at this tree, this 3D composition, what is the edge cover of X, Y, Z? How many atoms do you need to take to include? 2. You need to include R and S, or R and L, whichever you can include. If you do this, the first one leads to the tree width. The second one leads to a notion which is called the hyper. Actually, it's called the generalized hyper-tree width. This is your Gottlob's notation, and I tell you my critique generalized hyper-tree width. And how would you do it better? What is an even better measure that reflects the fact that we're going to use the worst-case optimal join and not a naive. By the way, this reflects a naive way to compute each bag, where you simply join R and S, or you simply join T and L. What would be a metric that corresponds to our more advanced method? The fraction, so we need the fractional edge cover. Fractional edge cover.
There's a min there implicitly, right?
The min is here.
I mean, for the cost definition, like you're saying it's the minimal effect.
Yeah, this is you're right. The minimum edge cover. This is the minimum fractional edge cover. Or alternatively, you can say the fractional edge covering number. Fractional edge covering number is a minimum one. Yeah, and if this is what you define, then the fractional edge cover here is what you expect. It's 3 by 2. And of course, you can define it even more. If you have cardinalities, then you don't need to stick to the fractional edge cover, which assumes all cardinalities are n. You refine it to what we know, to the Asian bound.
So what are the restrictions on C?
None. It has to be monotone, I guess. But
It's already not. It's not monotone already.
It's not monotone. It does not have to be monotone. Yes.
So the reason why the definition using max works is because now you have an acyclic tree, so it's O of input plus output, and then input is just going to be the max of all the individual ones.
Correct.
Okay. That
Yeah.
makes sense.
Yes.
Yeah, I also want to point out that we have a really good talk recording from Silence by Reinhard Bethler on all of fractional general hypertrophy with all of the terminalities. It's finally really helpful.
Can you send the link out?
Yeah, I'll do it afterwards.
Right. So I want to tell you 3 things, and let's see. Okay, well, I'm going to erase here because we no longer need this. So let me start by telling you something I don't know. So if you take a standard graph, P and E, which is not hyper. Consider okay, we can define two tree widths. So one is a standard tree width of D and E, which corresponds to the cost being x minus 1. Or we can define the generalized hyper tree width of D and E, where the cost is the minimum edge cover. So to give you an example, let's take a concrete example and see what would be a good tree decomposition. Give it a cycle. How would you construct a tree decomposition for a cycle? You worked on this, yes?
W or X, Y, Z, Y, Z, U. Wait, no, is it, no, it's X, Y, Z, Y, Z, X.
You put like one of them in all of the bags, and then you do like the chain.
Yeah.
Perfect. So let's start with X, Y. Let me first do a wrong one. So then you continue with Y, G as if it were basically DU, UD, DW, and WM. And now we need MX, right? Because we also need to include the edge MX. So what's wrong with this decomposition? X is not connected. So the fix is you just add X everywhere. And then it's connected. So what is a tree width? The tree width of, this is a cycle 6, 7. So this is exactly C7, the cycle of length 7. It's 2, exactly. What is a generalized hypertree width?
With allowing fractional or not allowing?
Not fractional, that's not that one. If you allow fractional, I don't know how many, we discuss this model.
Also 2, right?
It's also 2. Yeah, so in the case of when this is, when E is a standard graph, what can you do? So this is, yeah, you still cover this. By the way, what is the fractional hypertree width of C7? I don't know. Over this one.
You have to have
One half each one, right?
You think it's 1/2?
you have to put the you have to cover each node, right?
Yeah.
It's not covering the graph.
It still has to be 2.
It's good. If you look at this guy, for example, VW. So we have VW, but we also have X. So we have this edge that covers both of them, but X is by itself, so you need to choose another edge. And I don't see anything smart you can do. So this is also 2. Here it gets more iffy, but look at these two. Are these two always the same? It's a tree width, which is defined as a cardinality of number of variables minus 1. Always the same as the generalized hypertree width when we count how many edges we need to cover that set. And I don't know the answer, but I can tell you how I struggled with this when I was preparing your homework. And I was giving you this setting and the grid, right? M by N grid. Let me draw it like this. So if this is M and this is N, what is the tree width of such a grid? The backs here, in case you forgot, the backs look like this. They are like that. This is a back. And you move from one back to the next by essentially decreasing this edge. And when you reach the bottom, then you move to the next column. And now you increase back and move to the next column. Sorry? The min of M and N. Yes, because here I have M plus 1. And of course, you could change that. So it's going to be the minimum of M and N. But I have no idea what the generalized hypertree width is. The issue is that when you have a bag, and here you have many variables, the tree width essentially assumes that you can cover. So here is the issue. If all of them belong to edges, then I only need to count the number of edges. But the tree width says we have to count all of the nodes minus 1, which is much bigger. But at least we prove something, that namely that the tree width is greater than or equal to the generalized hypertree width. But are they equal? I don't know. This is why I modified the homework to ask you for the tree width, because I don't know how to compute the hypertree width.
I think Rainer might have some answers to this in his talk. I don't know if you're.
I think I asked him, and he didn't know. How told me something. He pointed out that you can have an acyclic query, or you can have the notion of acyclicity changes. But it's a naive answer, because we know that if you have a cyclic query and you add one big atom that contains all the variables, suddenly it becomes acyclic. But I don't care about the big atom. I only want these binary relations. But maybe even here, maybe it's better because here, each bag I can cover with fewer edges. So maybe the answer is 3. Okay, the second thing I wanted to tell you, which is super important in practice, is how do we compute it? So given a hyper graph, now it's really hyper. How do we compute the generalized hyper tree width of H, or even better, the fractional hyper tree width of H? And this is where Reinhard Fischler's result was so surprising. He proved that the problem, given H, check if the generalized hyper tree width of H is less than or equal to 2, this problem is NP-hard. And same for the fractional hypertrees, which essentially means it's hopeless. It's hopeless to come up with like the definitive algorithm that computes the best 3D composition. Now, of course, he has, I mean, to get hardness, you need to look at hyperedges, which are extremely wide. He has many special cases in that paper that are computable in polynomial time. But I think, yeah, it's a result to keep in mind before you get to the special cases which are tractable.
But we don't need them.
Sorry?
We don't need necessarily, I mean, I assume where we're heading is that, you know, given a, I guess it's not the fractional hypertree width, because it might not be like the best one, but given one, we can achieve, you know, we can run this algorithm to get performance that is better than both worst case optimal and practice.
Yeah,
right?
so what you're saying is any fractional, any 3D composition is better than none.
I'm asking, is that true? I mean, certainly the best one is better than both of those algorithms, but like, how good does your decomposition have to get to be better than both of those algorithms?
Yeah, no, it's a good question. I don't know. I don't know how much, but I have something to tell you. Yes.
Are there any like
if you throw everything in one node, right? Like you just get like the word is like the dumbest tree composition you can come up with is still like one of those algorithms, right?
Yeah, but I want one that's better. I mean, I'm hoping for an algorithm that runs better than both. Right?
So anything better than all in one minute.
I mean, then it seems like if you come up with any tree composition that follows those rules, it would be better just like even the worst one, which is just throwing everything in one bag, that would be just worst case scenario, worst case stuff.
What is it for C7? If you throw everything in one bag. And sorry, 3.5. I think it's 3. Yeah, it's 7 by 2. So n to the power 7 by 2 because each edge you can cover it with 1/2. And if we don't throw it, if we do this 3D composition, what is the complexity? 2. It's 2. So this would be n squared. So you have a very good point. Much better to do it in n squared plus output than in n to the 7 by 2. Yes, Remy?
So if you decompose a triangle, you can get worse, right? So if you take an edge out, then that becomes n squared instead of n to the 0/2. So it's not always standard to decompose.
Yeah, but that is not a correct decomposition, no? Because you don't.
What's it not right?
You need to include somewhere that edge that you have taken out.
So it's 2 bags. So one bag has 2 edges, and the other bag has the one edge that you take out.
I don't think it works.
Remember what edges go in the bag is induced by what nodes are in the bag. So the
yes.
definition is placing variables in bags and then.
Oh, so I mean, so one bag is X, Y. Oh, X, Y, Z already has all the variables.
That's right, yes, you don't get to choose whether or not an edge goes in there, it's
That's right.
chosen for you.
But I guess, are there like 3D transformation rules where you can start with something bad and then you transform it? Or like it's not obvious how to get from that to that?
And then I think the notion of hyper-3 decomposition was introduced by Georg Gottlob. This was around early 2000s. And he actually, from the very beginning, he introduced a slight variation in the definition, where he adds one more condition, which I don't remember. And he called, and so it's a restriction of what trees you can construct. He called that width, he called it the hyper-tree width of the hypergraph. So that is a hyper-tree width according to his definition, while this one is a generalized hyper-tree width. And this one can be computed in polynomial time. And the immediate reaction is, well, if you impose some restrictions on how you compute it, you look at the algorithm, you know, your greedy algorithm, whatever is computing, and you say only outputs of this algorithm are the right ones, then you can always compute something in polynomial time. But it's not like this. You prove something stronger. So the generalized hyper-tree width is, of course, can be better than the hyper-tree width. But this one cannot be worse than 3 times the generalized hyper-tree width. So you can't get very, very bad. Yeah, these are very, very deep results.
Is there anything known about fractal?
As far as I know, no. I don't think anybody understands how to generalize the hyper-tree width. Now, my quibble is, I don't like to call this generalized. I don't care about Gottlob's condition here. And I had this argument with Rainer Fischler, and you will hear me calling this hyper-tree width, period. No generalized.
Oh, they're restricted. The other one, they're restricted.
The other one, they're restricted, yeah.
Is that very tight? Or is that?
I don't know. It might be +1, three generalized 3 with +1. I don't know. Yes.
I think this is related. I was going to ask, are there any results of like better approximations that are computable in like polynomial time than just the hyper-tree width?
Yes. So this latest paper, which is very recent, by Rainer Fischler and Georg Gottlob, where they proved the hardness, has a long extension where they show that if you impose restrictions on your queries, which are very, very reasonable, then you can compute optimally the general hyper-tree with this one in polynomial time. And the restrictions are of the kind, if you fix a bound on the arity of the relations, then you can compute it in polynomial time. If you promise that all relations will have arity at most 4, then it doesn't matter how big the query is, you can compute it in polynomial time. Don't ask me how. They looked at other things. If you restrict how many times a variable can occur, then you can also compute it in polynomial time. So they really completely solved all the questions you might be able to ask.
So if you're trying to decide, do I use which algorithm do I use in order to compute my query? Is there like a nice way, like a meta algorithm to select between the two?
So Remy can answer this. I have no idea.
So
I mean, this is the better algorithm, right? Like,
yeah, so
Are you, I mean, assume, like if you don't know sort of like which one, like what you can't calculate with, you can't estimate the hyper-tree width more than some amount of accuracy, right? So you want to just figure out like which algorithm do I use? Is it like now the problem is not what is my hyper-tree width? My problem is like my hyper-tree width greater than or less than some threshold. Is that an easier problem to solve?
Yeah, so the decision problem doesn't get any easier. So this is what you want to look at. But can you at least decide if the hyper-tree width is small or big, and you can, I mean, without any restriction whatsoever, you cannot decide this about it.
So these were, but you can in this restriction. Whatever, what
Yes.
is these reasonable assumptions?
Yes, and in the restricted case, it's not just that you can decide, but you actually give an algorithm, which might be the same one. I don't remember. It might be exactly the algorithm that computes the original algorithm that computes a hypertree width, which is very simple actually. It's the bottom up or a top down. I don't remember. But I remember it's very simple. It has this little hack. You wonder why should I adopt this little hack? And I think the same algorithm works out of the box. And guarantees to compute the best generalized hypertree decomposition if we impose these restrictions. This is what I remember from Reinhardt's talk.
And is the simple tree width, is that also computable in P time?
No, this is the tree decomposition. This was studied well before databases were interested in this. It's a topic of mathematics, graph theory. And two things to know. First one is his name called Bodlander. And I don't remember if there is an E somewhere here. Bodlander. What he proved is that given K, checking if the tree width is what you want to check, if it's less than or equal to K, is in B time. I said it incorrectly.
In P time with respect to K as well, or?
No, for any K. For any K, checking that the tree width is less than or equal to K is in B time. And that P time depends in an exponential way in K. I don't know how it depends. And also that checking, computing the optimal tree width is again a hard problem that I don't remember how to state. Yes.
Is there like a general meta theorem that relates the hardness of like CSPs and these kind of like algorithms to tree width? Because I know like in SAT, like tree width is important for tractability in a certain way as well.
Yeah, so tree width is used in SAT and all sorts of CSP questions, but I think you're asking for the opposite. In the model CSP using tree width. And this I don't know. It's an NP-hard problem, so we can capture any NP-hard problem. But Reinhardt-Fischler's proof is very complicated. So I wouldn't use a tree width as a substitute for SAT.
So is this how we should be running our queries? Evaluating our queries? Like, is this
Absolutely.
So the best we can do right now?
I think so. But you can always use a joint, a standard join. But if you look carefully, what happens here, it's essentially a tree decomposition. This is what it does under the hood. Now, if you how would you compute such a join query? Well, you start joining, this edge with that edge, and you can project out. Once you join with this, you don't need y anymore. So it looks like you start with xy, you join it with yz, and now you can project out. What do you need to retain? Well, you need to retain both x and z because you need x later. So now you can join with zu. Yeah. And again, you can project out on x and u and continue the join.
It's going to violate the, isn't this going to violate our connectedness?
No, because you keep x everywhere. This is
on the other side, or I guess.
So you can throw, as you continue this join, you can throw away the variables that you don't need, but you need to keep the original variable in order to close the loop. Because at the very end, you're going to join with wx. And this is when you need the x to do the join on x. Now, there is a long discussion whether database systems actually do these projections early, and most of them don't. But in theory, tree decompositions can be captured as query plans. The only question is whether database systems push projections down. And actually, Remy investigated this, and here's a theory for why they don't push projections down. So I can tell you that your theory, and I can tell you Thomas Neumann. Your theory was that it messes up with the cost-based optimization of join reordering. This is what you learned from what's the name of the company. And, I'm blanking now on the name of this. They are building this distributed database system. Cockroach, yes, Cockroach DB. So you talk to Cockroach DB and they told you that we don't push projections down because this messes up join reordering. The standard system R algorithm does dynamic programming. But Thomas Neumann claims that you don't do this in Hyper, and Umbra doesn't do this because each duplicate elimination is costly. You're adding additional cost, and it's not clear that this will pay off. Good, folks. That was a lot for a lecture without a topic. So I see you then on next week. We start data log. Please start thinking about your projects.
Do you think Hyper and the like will adopt agreement based for an optimizer?
Hyper is gone. Hyper is out of Thomas Neumann's hands.
But I mean, a real database system